Okay, so let's begin. Okay, so in the previous lectures, in the previous two lectures, we did some amount of combinatorics, right? How to count. That's exactly what we did. And for instance, if you remember, we did this binomial coefficients, how to count the same set in two different ways and things like that. So this lecture and the next couple of lectures will be about trying to understand sets, right? Sets and their sizes. What can we say about sets? What operations can we do on sets and so on? So the first few lectures, at least the first 15-20 minutes will be like really basic. So if you have seen any set theory in high school, it should be a cakewalk for you. But slowly we will build on these just to ensure that everybody is in the same pace. We will do basic set theory. Okay? So when we talk about sets, you can think about them as a collection of objects, right? Some collection of objects. And you may have seen examples of sets in school that contain 3 elements, 5 elements, and so on. And this notation is called the set builder notation. Okay? This way of enclosing the set in curly braces is called the set builder notation. And by this symbol, we will denote membership. That is, you say A is in the set S, and this symbol to denote non-membership. For example, D is not in the set S. Okay? This notation is usually called the set builder notation. And usually sets that you have seen usually enclose all the elements that belong to the set within these curly braces. So some interesting things about sets that you would have probably already seen is that there is no redundancy in sets. So sets do not contain redundant elements. So for example, if somebody tells you 1, 1, 2, 3, that's essentially the same set as 1, 2, 3. So you can think about sets as a collection of distinct objects. For example, the set of all students, the students attending this class, they form a set. The faculty who teach you, we form a set, and so on. And another thing to remember about sets is that there is no ordering that is assumed when you think about the elements in the set. So sets generally are not ordered. So if you look at A, B, C, that's the same set as B, A, C. Right? But there is a notion of ordered sets that we will see sometime later on in the course. But at least for the next few lectures, we will assume that sets are not ordered. Sets, when you use the term sets, there are no redundant objects in the set, no redundant elements, and sets are usually not ordered. And every object in the set is usually referred to an element of the set or a member of the set. These things you may all have seen. There's nothing new about all of this. And there are several ways to describe a set, right? For example, if you look at the set 2, 4, 6, 8, 10, I can also describe this as all x less than or equal to 10, let's say greater than or equal to 2, x mod 2 is equal to 0. Right? So there are several ways in which you can describe a set. And these two sets are essentially the same. So when you say that these two sets are the same, in this example, it's very easy, right? You have to just ensure that 2 is on the right hand side, 4 is on the right hand side. But in general, when you are given two sets, it might be difficult to figure out whether they describe the same set or not. So that is something we will see in this lecture. Okay. And another important concept or notion that you have seen is that of subsets. Right? For example, if you have two sets A and B, then you say A is a subset of B if every element in A is also an element of B. Okay. So elements of A are also elements of B. For example, this set is a subset of, let's put this, A, B, C, D. Right? And you use this notation to say that A is a proper subset of, which means that there could be elements in B which are not in A. For example, even here, right, there is D, which is not in the left hand side. Okay. So you call A a proper subset. Some textbooks use this notation, so we'll use them interchangeably, whichever is convenient. So So some things to note are, what can we say about any set being, any set is a subset of what? Every set is a subset of itself. Right? So A is a subset of A itself, because what we want to say is every element of A is also an element of A, which is true. And if you look at the null set, that's a subset empty set, right, which is denoted by this. I think we panned out. Let me try to figure out. Yeah, I think it just panned out. I need to remove this. Just undo. Okay, wait. Yeah. Yeah, now it's fine, right? Now you can see the screen, right?
Yes, ma'am.
Yes, yes. Okay. So the empty set, which is denoted by this, is a subset of every set.
Ramya, sorry, I'll just interrupt you for a second. Students, you people, you are joining very, very late. So from the next class, we will not allow you. This is 5:10 now, and still some people are joining. So please maintain that from the next class itself.
Yeah, please join. I mean, we cannot repeat everything, right? So you may also lose content. So, and we should also be around. The other instructor has to be around and keep admitting people. So we come. Okay, so this thing that we saw, right? How do you show that two sets are equal? So if I give you two different descriptions of the same set and ask you whether they are the same or not, then how do you show? You want to show, suppose this is the set A and this is the set B. One way to do this is that you want to check if every element of A is an element of B and every element of B is an element of A. So essentially you say that sets A and B are equal if A is a subset of B and if B is a subset of A. And you may have seen several operations on sets. Some examples of operations are union, intersection, and so on. So if you have two sets A and B, then A union B contains all elements in A and all elements in B. And you will, whatever is in both, you will represent it only once, because we assume that sets cannot have redundant elements. So these are elements either in A or in B or in both. And the intersection is denoted by A intersection B, which means elements in both A and B. Okay. So another operation on sets is that of Cartesian product, which is A cross product B. So you have two sets A and B, which may have like several elements. Then this set is set of ordered pairs. So now ordering comes into the picture, where A is in the set A and B is in the set. So these are all like very basic things you may have seen in school. Like no big story going on there. Okay, so now we want to talk about counting sets, right? Or you're given a set, you want to estimate the size of the set, just like what you did in last class. So the next two lectures will be about understanding the size of a set. So if there are any questions here, yeah, you can ask. I hope you have seen all of this already in school, but still. Are there any questions? Okay. Yeah, I hope you have seen all of this. If you have any questions, please ask. Okay, so now let's move on to size of a set or cardinality of a set. For example, let's say we have a set S, which we used last time. Right? So now what is the cardinality of the set? It's the number of elements in that set, right? And you denote it by this, like the mod operator. And this now is 4. Right? There are 4 elements in this set. So now, suppose you're given a set S, and that set is a finite set. Then the cardinality of S is the number of elements in it. So when you said that the number of elements in S is 4, how did you do this? Or let's take this set, which is A, B, C, D, E. Right? So the size of the set is 5. Now you have to say how did you say that the size of the set is 5? How do you argue?
It's in bijection with a set of like with 1 to 5.
Right. So what you do is just like you count in school, right? In kindergarten. So you look at A, this is the first element of the set. You look at B, this is the second element of the set. C, which is the third element, D, which is the fourth element, and E, which is the fifth element. So to every element of the set, you assign a number. It's a natural number, a unique natural number. So you don't assign 1 to both. If you did assign 1 to both A and B, then you would have gone wrong in counting. So what is the process of counting that we did in school? Right? It is essentially associating a natural number with every element of the set. That is what the process of counting is. Right? That's what we do always. If you're given a set of apples and somebody asks you to count it, you take every apple from the basket and give it a number. Right? So whenever you're given a finite set and you want to count it, right, you have to essentially assign a number. So if somebody gives you a set and asks you whether this set is finite, you say the set is finite if there is a one-to-one correspondence between the elements of the set and the set of natural numbers for some bounded subset of natural numbers. So you say a set S is finite if there exists a one-to-one correspondence. You can think about this as an assignment or a mapping between the elements of the set and the set 1, 2 to n for some n. Right? And this index, this number n, is called the cardinality index, which is denoted by this number n. Correct? And the cardinality of the empty set is just 0. Is this clear? Yeah, this one-to-one correspondence is something we haven't like explicitly defined what it is right now. But yeah, at least you can think about it as an assignment of natural numbers to elements of the set. And what is an infinite set? An infinite set is a set that is not finite. So what does that mean? Right? That's not clear yet. What is a finite set is clear, but what does it mean to say that a set is infinite? You're just saying that it's not finite, which means that you must not be able to assign natural numbers to a subset of 1 to n. Okay? To the elements of S, you should not be able to assign 1, 2 to n for any n. Okay? That seems a bit strange at the moment. Okay, so now we know how to estimate the cardinality of a finite set. So if I give you a finite set, you know how to estimate its size. You have to just assign numbers, natural numbers, a unique number to every element in the set. All right. So just to brush upon what Partha did last time, to go further, we may need the notion of functions between sets. So let's say you have two sets. These are things you already know, but still, right? A and B. Now you can define functions that map elements of A to elements of B, right here and there. And you say a function is injective if it is one-to-one. Just writing 1 to 1. Right? That is, if f of x is equal to f of y, then x should be equal to y. This is what we mean by an injective function. But it might be that some elements of B are missed out in this map. Right? So an injective map, some elements of the range may not have pre-images. But if every element of B has a pre-image, then you call that function surjective. Or it's sometimes called an onto function. For every y in B, there exists an x in A, such that f of x is y. So here f is a function from A to B, where the domain is A and the codomain is B. Yeah. And you say f is a bijection between A and B, or from A to B, if f is both an injection and surjective. F is both injective and surjective. We say bijective. Surjective. Right? So now you can replace this one-to-one correspondence, right? Unique number you have to map. So you can replace this with if there is a bijective function, right, between S and 1, 2 to n. So this whole text here, right? You can just replace if there exists a function f from the set S to the set 1, 2 to n, that is bijective for some n. Is this clear? Or if there are any questions, then we can agree this. So these three notions of functions should be like very clear. Otherwise, it will become messy. So if I give you a function, you must know what it means to say that a function is injective, a function is surjective, and a function is bijective. Is this clear? Okay, so now let's say you have two sets A and B. And there is an injective function f from A to B. Now, what can you say about the cardinality of A and B? So there is a function which is 1 to 1. So for every element of A, it maps an element to B. To every element of A, it assigns an element to B. But it might be that some elements of B are left out. So what can you comment about the comparison between the cardinalities of A?
Cardinality of A is less than equal to
Right. So if I give you two sets and ask you, is the cardinality of A less than or equal to the cardinality of B? Or otherwise, is A a smaller set? You just have to come up with an injective function from A to B. Similarly, let's say there's a surjective function f from A to B. Then what can you say if there is a bijective function? Yeah, you have to fill.
In surjective, cardinality of A is greater than or equal to B, cardinality of B, and in bijective it is equal.
Yes, so this is clear to everybody. Because in surjective function, to every element in B, there is a corresponding tree in each of B. So size of B must be at least the size. But it could be greater because the function could be many one. Right? Several elements could map to the same element. Is this clear? So if I give you two sets and ask you, are they both of the same cardinality? What you need to essentially show is you need to come up with a bijective function from A to B or between A and B. A function that is both one to one and on. Okay. So now in finite sets, everything is cool. Okay. So there is nothing great about finite sets. I mean, there are several great finite sets, but then if I ask you a set, give you a finite set and ask you to count, you can just sit and assign numbers slowly. Now the story becomes interesting when the sets are infinite. So can someone give an example of an infinite set? The first infinite set that you would think of.
A set of all naturals.
Right. So it's already there, right? The set of natural numbers. Right? Which is the set 1, 2, 3, and so on. And this set is usually denoted by n. So this set is an infinite set. There are infinitely many elements in the set. Right? So if somebody asks you what is the cardinality of the set of natural numbers, right? It's an infinite set, but can you somehow sit and count? Now, if you recall the process of counting that we did for a finite set, what did we do? We took every element in the set and assigned it a natural number. The same thing you can do even now, right? You can take 1 and assign it the number 1. You can take 2 and assign it the number 2, and so on. So you can order the elements of the natural set of natural numbers, even though it is an infinite set. Okay? So in other words, this set is said to be countable. That is, it might be infinite. It might be that there are infinitely many elements in the set, but you can still count the number of elements in the set. What do we mean by we can count? Whatever we did in the process of counting. Right? We assigned a natural number, a unique natural number to every element of the set. So you say a set S is countable if S is finite. So if S is finite, it certainly is countable, right? You can assign a unique natural number to every element of the set. Or it might be infinite set. But if that is the case, then there is a bijection between the elements of this set S and the set of natural numbers. Or if there exists a function f from S to n or from n to S, right? There exists, let's say, let me just write it in English. If there exists, oh, by the way, this is there exists a bijective function or a one-to-one and on-to function or one-to-one correspondence between the set S and the set of natural numbers. Then you say the set given set S is countable. And some textbooks for this portion, right? So either the set is finite. So if it is finite, it certainly is countable. Right? This is what we saw in earlier examples. But if the set is infinite, then you have to define a notion of counting, right? A cardinality for that set, for the elements of the set. And that is defined by coming up with a one-to-one correspondence between the given set and the set of natural numbers. And in this case, when the set is infinite, some textbooks call this countably infinite sets. I'm just mentioning this in case you refer some textbook. So they say a set is countable if it is finite or if it is countably infinite. It is infinite, but it's still countable. That's what they want to say. So the set of natural numbers is always countable, the way we think about it. And if you ask what the cardinality of this set is, it is denoted by this symbol. It is called LF naught or LF null. Just a symbol to say that this is the cardinality of the set of natural numbers. I don't know if this is written as not. So this is the first letter of the Hebrew language. So this whole notion of counting or story was defined very early, somewhere 16th to 18th century. This was done by Cantor. So he defined what countable sets are, when do you say an infinite set is countable, and so on. Okay, so is the definition of countable sets clear? The whole lecture and the next will be about countable sets. You can hear some echo. Actually, I don't know how to switch it off. If somebody knows, it must be good. Yeah, this little bit of volume that comes up in the iPad. Mute it. Okay, so if there are any questions about this, let me figure out. By any chance? Can you hear or not?
Ma'am, you're audible.
Okay. I will just try to share. Maybe I will switch off the video. Okay, so is the definition of countable sets clear? Okay, so now I hope it's clear. If it's not clear, please post on the chat. So now we'll move on to showing that several infinite sets are also countable. So the first set is the set of.
Then what you wrote about this LF null, I didn't get your word. voice at
Yeah,
that
so
time.
this is just used to denote. Okay. Yeah, I will repeat. Okay. So now, we say that a set is countable. You mean that there is a bijective function between the set S and the set of natural numbers, right? So if somebody gives you an infinite set and asks you what is the cardinality of the set, right? Is it countable? As soon as you show that it is countable, demonstrated, what will you do? You will come up with a F between S and M. But you immediately know that this set S has the same cardinality as the set of natural numbers, right? From observation, because there is a bijection between S and M. So then you need to think about what is the cardinality of natural numbers. You could always denote it like this, but people use this symbol. It's a special symbol that is used to denote the cardinality of natural numbers. So some textbooks you might see that the set S is stable and its cardinality is LFI, which means that the cardinality of the set is the same as the set cardinality of the set of natural numbers. So in fact, one way to think about countable sets is you say a set is countable, an infinite set is countable if it has the same cardinality as the set of natural numbers, because natural numbers are the most straightforward way to count elements of the set. Is clear? No? I hope my voice is clear. Okay. So now let us look at some more examples. For example, let's look at S to be the set of odd positive integers. The set 1, 3, 5, 7, 9. So now is this set S countable? It's an
Yes, ma'am.
infinite set,
Yes, ma'am.
but can you still count it? Okay, so can someone then come up with a bijection? So what you have to do is you have this set of natural numbers. You have to find a map, right, between these two sets.
2n minus 1.
Yeah, so you can just do this. And you can also argue that this set, this function that you just constructed is a bijective function. Okay, so this I believe is sense. So what do we have? We have n here, which is countable just from definition. And then you have set of odd positive integers, a superset of integers. Now let's just look at S, which is the set of all integers. So is this countable? So you will have 0. And you will also have, you will have to. So what are you doing when you're saying that a set is countable? You are essentially giving an index for every element of the set, right? In order or enumerate the elements of S. So the goal when you want to show that S is countable is to somewhat enumerate or list the elements of S in certain order. That is, in this list, the first element is 1. In this list, the second element is 3, and so on. So the countable sets are sometimes called denumerable sets, because you can actually enumerate them. So now that's the same thing that you want to do with the set of all integers. Is this, in other words, can you assign a natural numbers? So let's say you assign 0 to the natural number 1. What is the next thing that you do? To which one can we give 2? So the goal is clear, right? 1, 2, 3, 4, so on. You have to keep assigning numbers to this set. So this is your set S. And this is the set of natural numbers. I'm just trying to come up with a bijection. Can someone give a bijection?
Am I audible?
Yes, yes.
Yeah. So you can take the non-negative numbers to 2n and the negative numbers to minus 2n minus 1.
Hmm?
You can take
And then
the
what about 0?
Yeah, 0, I count that in the non-negative numbers.
Okay. So you can do this, right? So 0 is to 1, and then this is 2, this is 3, this is 4, it's 5, and so on. One sort of ordering like that. So what he says is exactly this. So this f is a function. S to the set. S is actually the set z. So z. So z. And just as what he pointed out, so might be either greater than 0, x is less than 0, or x is 0 brings on to 1. With this case. So now we need to show that this is a bijection. So I'll do one example and then everything that explicitly comes. So to show that f is a bijection, we first need to show that f is in Z. That is, if f of x is equal to 12, then x has to be equal to 1. But in this case, we need has to be some 2x is equal to 1, which means that x is equal to 1. Or 2x plus 1 is equal to 2. These things you can do. And then you have to show that f is subject. So if such a question comes up, this is how you do it. Yeah, I will try to. Just give me 1 minute. Hope this time it only is clear. Sorry, okay, I'm not sure what. Maybe there is some internet issue. But is it clear now? Yes, no. Yeah. Even now, can you not hear?
Yes, ma'am, now it's clear.
Okay, yeah, we'll just share. Yeah, please let me know if it's not clear. Yeah. We'll just go. But until this, it was fine, right? People could do it. I hope. So to show that f is subjective, we have to find what the inverse of every element. So x might either be odd or x might be even. So if x is odd, then you have to clearly write down what f inverse of x is, which in this case is as he pointed out. And if x is even, then you have to say what exactly it is. So this shows that you have constructed a bijective map between S and the set. So the set of all integers is counted. So we had.
Ma'am, shouldn't it be minus 2x plus 1 for x less than 0?
Oh, okay. Yeah, so these things will also change accordingly. Is this fine now?
Minus of 2x plus 1, I guess.
Please. Okay. Yeah, please verify. And then this thing also. I can just put dash here so that you can put it up.
Ma'am, so can I ask a question, ma'am?
Yes, yes.
So if we want to count the number of primes, then like
yeah, we will come.
Okay.
Yeah, yes, that's the most natural thing, right? So what are we trying to do? Slowly, the story should build in. So you have set of natural numbers here. Then you have set of integers. Then you have set of rationals. reals. And then there are other nice numbers like what he said, primes, irrationals, and so on. So we want to understand, can we enumerate all of these numbers? These are all infinite sets. So what can we say about the cardinality of n and the cardinality of z? So one important thing is, what can we say about primes? One natural thing is, suppose somebody tells you that the set of primes, show that the set of primes is countable. What will you do? You have to come up with a bijection. So one thing you can do is you enumerate all the primes. For the first prime number, you give the assign the number 1. For the second prime number, you assign the number 2, and so on. So you have to do this consistently, and you have to explicitly write down what the bijection is. So there is some trouble, but we will see this. But this we will see in the next lecture. You have to wait. Okay. So now, I hope you are okay with it. It's a very simple statement. The moment the statement is met, you will be able to see. So now n we know is countable. So just color it like this. Z also now we know is countable. So the next natural question is, what can you say about Q? What is this set countable? So let us do that. So, but before that, there is something very interesting about what we did so far. I want to see if somebody is seeing. So now, what can you say about the set n and the set z? What is the connection between these two? What is the relationship between these two sets?
N is subset of Z.
So n is a subset of z. And is it a proper subset? Like, are there elements in z that are not in n? There are, right? Negative, all negative integers. So then, what would you be your first guess about the cardinality of n and the cardinality of z? Suppose you had two finite sets A and B, like this one, A, B, C, which is A, and B, which is A, B, C. You know that A is a proper subset. This immediately tells us that the cardinality of A is less than or equal to the cardinality of B. In fact, strictly less. Sorry. Yeah, that is it. But the cardinality of A is strictly less than the cardinality. Now, you know that the n is a strict subset of E. But from whatever you show, right, that n is countable, which is what the cardinality of n is. So the cardinality of n is L of naught. Now, what can you say about the cardinality of Z? Compare it to the cardinality of n.
It's equal to n.
It's equal to n, which is L of naught. This is something strange, right? Something that did not happen in finite sets. When one finite set is a proper subset of the other set, you definitely know that this set must have much less strictly less cardinality compared to the others. But these two sets being infinite, even though one is a subset of the other, the cardinalities are the same. Mathematically, this might seem like something strange. But is it that strange? So n is an infinite set and z is an infinite set. So what can you say about infinite sets in general? What are you doing? You're taking n and then you're adding more elements to it, which is already an infinite set. Right? So if you add more elements to an infinite set, the set will still remain infinite. That is what this observation is telling you. So this you can actually formalize. So this is the first difference that you see between finite sets and infinite sets. That if you have a set A, is a proper subset B, A being finite sets. Or in other words, let's say you have a set A, let me just write it like this, which is a finite set. And there is an element B that is not in it. We look at the set A.
Like we just associated a bijection between Z and N, but we can obviously see that the negative integers are not in N. So like that kind of says that the cardinality of N should be less than Z.
No, right? That is what I'm saying. Yeah, so that's what. So that is what the intuition said, just like what we said. So there are negative integers that are not in N. So by throwing in negative integers into N, the size of N should only increase. But somehow suddenly we have demonstrated a bijection which shows that the size of both the sets are the same. Right? Why is this true? This is true because the set N already contains infinitely many elements. So if you add one more element to the set, it won't change anything. This is the difference between finite and infinite sets. So in finite sets, If you throw elements into a finite set, the set becomes bigger, becomes larger in size. But since an infinite set, a set already has infinitely many elements, throwing in new elements will not change its cardinality. The set growing does not really mean grows into what? It just grows into infinity. So whatever I said in English can actually be formalized like this in math. Maybe still if you have questions, then let's. So if you have a finite set A and you add an element B, the cardinality of A union B is cardinality of A plus 1. So let's say A is non-empty. Then definitely this is greater than the cardinality. But now, if A is an infinite set, yeah, along these 2-3 lectures, you will see a lot of differences between finite and infinite. There are so many very natural things that happen in finite sets which don't hold in infinite sets. They behave very differently from what we actually do. So if A is an infinite set, and let's say B is an element that is not in it. So you can think about A to be the set of natural numbers and B is a negative integer. The cardinality of A union B is exactly equal to the cardinality. Right? So if I claim this, when you first look at it, it might seem like it's not true, right? Like what he said. You can actually prove this. Okay, so maybe you should go ahead and prove it, and I will write down. Okay, so how do you show that these two sets have the same cardinality? You just said. What should you do?
By contradiction, we can assume it like if it is greater than or.
No, but to just show that two sets have the same cardinality, the set on the left and the set on the right has the same cardinality. What is one way to do it? What you said is true. It might be that you can assume it is greater than and then try to find it. But we just saw one way to show the two sets, any two sets have the same cardinality. You have to demonstrate a bijection from between A and B, right? That will show that these two sets have the same cardinality. So I have to come up with a bijective function. Okay. So from A union B. So on one side I have A union B, the other side I have. So A union B has B and then some other elements of A. So by the way, I must have said something which I did not. But when I say A is an infinite set, for this statement to be true, A should be a countable set. I mean countably infinite. Yeah, I should have said this earlier. I mean that A is a countably infinite set. Right? For example, N we think of it as a countable set. Now we are throwing negative numbers into it. One, right? There is this element is 0. And because it's infinite, it has another element, A1, and so on. So all the elements are infinite and it's countable. So there is a bijection between A and the set of natural numbers. Now you want to construct another bijection from A union B to A. So can someone try to come up with a bijection here? But is the goal here, even if you are not able to construct a bijection, is the statement
AI maps to will map AI to AI plus 1 and B to A0.
Right. So what is the most natural thing to do? Whatever he suggested. Map B to A0, and whatever A0 went to, map to A1. Whatever A1 went to, map to A2. Right? So this you can actually explicitly write down. So now to show that these two have the same cardinality, I must demonstrate a bijection. And here is the bijection. That's what he said. Right? So you construct a function F. So you actually want to construct a function between 1, 2 to n and A union B naught, right? So what you want to do is here you want to assign numbers, natural numbers here. So like what he said, you can assign 1 to B. And what is a natural number you assign to A? Whatever was defined by the bijection from n to A. So you know that A is countable, which means this means that there exists a G between n and A. This is a bijection. Right? So to every element of A0, there was naturally another natural number that is actually assigned. Maybe this was 3, this was 5, this was 7, and so on. So now to B you assign 1, and everything else you shift according to G. That is exactly what the bijection is. So f of x, you can assign it to b if x is 1. And for every other thing x greater than 1. So what should 2 go to? Under f, wherever it went to with respect to 1. Because 1 you assigned off to b. Right? So that is gone. For the remaining elements, you have to assign natural numbers. Now you can show that f is a bijection. That is an exercise.
Ma'am, so it is a composition of 2 bijections?
Yes, so composition of 2 bijections is a bijection. So that is another thing which I did not do. Maybe wait. Okay, so show that f is a bijection, that's one thing. So one hint here is that you have to use the fact that G is a bijection. Otherwise, you may not be able to show. So this statement holds for countably infinite sets. Like what he said, composition of bijection is a bijection. Okay, so these exercises I'm giving up, but if you have any difficulty, then we will do this in the next lecture. But I just want you to have some practice. So there is one exercise here. This is the second exercise. So please get back if you're not able to do this. Maybe in the beginning of the next lecture. Yes. So is the claim clear? Like what is going on? Whatever was true about finite sets is not necessarily true about infinite sets. Like even though n has strictly less cardinality than z, strictly less is a strict subset of z, the cardinality of z and n are the same, essentially because they're infinite sets. If you add more elements to an infinite set, it's still be an infinite set. Is the story clear? So whenever somebody gives you a set and asks you to show that it's countable, all you have to do is you have to write down the elements of S in some order. Right? Come up with a mental picture. Okay, put this in the first place, this in the second place. Essentially, list the elements of n of the given set S in a nice order. Order the elements of the set S. Like for example, in Z, you did this zigzag order, right? This one, then this one, then this one, then this one. So you do this in paper and then try to write down the bijection out of it, whatever drawing you have. You can construct a bijection function out of it and show that it's a bijection. Okay, so now this is done and this is done. So what is your guess about Q? The set of rationals.
Countable.
Is it countable? So who said it's countable? Sorry, someone said it's countable. Yeah, okay. So why do you think it should be countable?
Oh, P by Q, then P comma Q ordered lexicographic, the Cantor diagonalization. Same thing.
Sorry, maybe I could not hear. You want to do something like this?
So P by Q is any rational number. If we consider P, uniquely identify each rational number with P by Q in the reduced form, then consider P comma Q pairs and order them lexicographically.
But don't you need that Cartesian product is accountable for this?
Yes. So Cartesian product is countable. Yes.
That is something that is needed, right? Which we haven't seen yet. So it's not clear. That is not clear. Though that's a proof. That is true. But if
that
you know
also
that the
uses that
product,
Cantor diagonalization.
Yeah.
I mean, one proof. Yeah. I know that also uses that.
But we have not seen Cantor's diagonalization also. So yeah, that is true. What you said is right. But let's try to order rational numbers, assuming we don't know anything that we have not seen in this lecture.
Ma'am, we can do triangular numbers.
Sorry, I could not hear the last one.
By triangular numbers.
What do you mean by triangular numbers?
Like I into I plus 1 by 2. No, I think I forgot, but like we can something with I and J. So,
where it's I by j, is it? The rational number given is I.
Yes, ma'am.
Right. Okay. So it's something similar to that. Let's just look at the first thing. So those of you who have already seen this proof, for a minute assume that you don't know. You are too new to this class. So somebody
we
said
could-
something. Huh.
We could try reducing every rational number to its lowest form and then just
Rational
order
number to
them
its what?
lowest form, like
Reduced form, right?
Yeah,
Correct.
reduced form, and then we collect all the same, like collect all rationals of the same denominator, and then send them to a single, the entire set of rationals with the same denominator to a single natural number. And since the denominators themselves are like they are essentially just n, so what we get is just a bijection from q to n.
That is right. So how do you write this as a proof, right? Whatever you said is perfectly right. Whatever all of you said is actually right. But we are just trying to see many different ways of doing the same thing. So it is true that the set of rationals is countable. So I will write the verdict here. Is countable. So Q is countable. But if somebody actually began the first way to do it, right? So you have A by B. Let's say A is here, B is here. These are numbers. So one thing you would try to do is, okay, so I have these set of numbers, 1, 2, 3. These are all actually rational numbers, 1 by 1, 2 by 1, 3 by 1, 4 by 1. So now suppose like what someone suggested, you can give the number 1 to 1 by 1. And then you want to assign the number 2 to the next element. So what do? You figure out what is the next element. Maybe you can try to give it to 2 by 1. But then you figure out that there is a number between these two, which is half. So maybe to that you have to give the number 2. That is your second element in the list. But then again you figure out there is a number 1 by 4. Maybe that is the second element in the list. Right? And so on. So there are infinitely many rational numbers between any two rational numbers. So this way of drawing it in a line and trying to order it won't work. So you have to come to reduced form, like what someone suggested. Right? That is the idea. But how do you do this essentially? So you write down the numbers in order, just like what you said, 1 by 1, 2 by 1, 3 by 1, and so it's 5 by 1. So these are all numbers with denominator 1. Let's just get some answers. Then let's write down numbers with denominator 2. So I'm just mentioning whatever everybody else said so that all of us understand. You've already, those of you who said the proof, it's right. 3 by 3, 4 by 3. We just write one more. Right? So now I have to start giving an order. These are all rational numbers. So the first thing to note is that every rational number appears in this table. So it's a table. It has infinite dimension. Right? It's a large table. But every rational number appears somewhere in the list. Okay. So now, just as one of the students suggested, you can. You give 1 by 1 the number 1. And then 1 by 2 the number 2. So you keep covering things in a diagonal fashion. So if you look at all the elements on a diagonal, they are all elements whose sum of the numerator and denominator is the same. So the sum of numerator and denominator is 1 here. The sum of numerator and denominator is 3. Then it is 4. Here it is 2. 5 and so on. So if you look at every numerator denominator, that's what we want to do. And the rational number definitely appears in a list. So if you keep ordering the elements in this table, definitely every rational number will be assigned some natural number. But there might be a problem like what he said. So for example, let's say this I assigned 3. So I came from here to here, then I went here, And let's say one here, just like how we did for integers. And when I come here, I look at this element. I realize this 2 by 2 is actually equal to 1 by 1, for which I've already assigned a natural number. Right? So to every rational number, we want to assign a unique natural number. So 2 by 2 is the same as 1 by 1. So we should skip it now. And then you can go ahead and continue. 1 by 3. Has this been covered? No. So then give it a number. 1 by 4. Keep doing this. Okay? And so when you come to 4 by 2, you will realize that it's already same as 2 by 1. And I've already given a number to it, the number 3. So you should skip it. Okay? So every rational appears somewhere in this table. And you have to skip common factors, the common numbers. That's exactly what someone had said. You consider the set of all rational numbers. You look at their reduced form. So you group them into bags, like 1 by 1, 2 by 2, 3 by 3. All of these are in the same bag. So you give it just one number. Okay. So now to actually prove that is countable, it might seem like very trivial, like what is there to say? You must first remember that if you're given a number p by q, you look at p plus q. And you go to that particular diagram. Definitely P by Q will be listed in that diagram, the P plus QF diagram. And how many elements are there in this diagram? There are countable many elements. Although it is infinite, that set is countable. So you can keep assigning numbers, natural numbers to each of them. And this will be a bijection. But now if somebody asks me, can you explicitly write down? Also here, I think I actually used Q plus, right? In this table at least. You can do this for Q, but here we only do positive rational numbers. So if someone asks me to explicitly construct a bijection, it is slightly difficult. So just by looking at P plus Q, if I have to explicitly come up with a function of P plus N, that is a bijection. It is a bit. So this will probably be a graded assignment. It is quite tricky. Just by looking at this, right? Even if so, this sort of a enumeration is also considered as a proof. So even if you write this, it's fine. Coming up with an explicit bijection, arguing that it's a bijection, will be slightly difficult. But there are other ways to show that a set is countable, which we'll see in probably the second or third lecture. You don't have to always demonstrate a bijection, because coming up with a bijection is really difficult. See, even though you are able to intuitively see that this set is countable, now if I ask one of them who answered to explicitly give the bijection, so what does P by Q go to? What is f of P by Q? This natural number here might be very messy. It might be a messy expression in P and Q. It might also involve P plus Q and so on. So coming up with an explicit bijection is a bit difficult, but there are other ways to show that sets are countable, which we will see next. But you must be convinced that this is a proof that convinces you that the set of at least positive rational numbers is countable. You can use the same thing to show that set of rational numbers. So is there any question here?
Excuse me, ma'am. Can we prove it by proving that n cross n is countable? Then any subset of a countable set is countable. If we can prove that, then we can prove we can take the subset GCD P comma Q is equal to 1, and
correct, exactly. So what is the first natural bijection that you can get from P by Q? It can just be P comma Q. Okay? So this is perfectly fine, because there is no question of reduced form here. So 2 by 2 and 1 by 1 are no longer the same thing. Even 2 by 3, for example, and 4 by 6, they are not the same. So this is perfectly fine. But for this, we need to show that n cross n is countable, right? That's what you're asking. Is that correct?
yes, ma'am. I asked that.
So this answer is yes. You can try to prove it. It's not at all difficult, but we can also try to do this in class, maybe in the next class. So coming up with a bijection from, so what do you have to do to show that it's countable? You have to get from n cross n to capital N. Yeah. So even here, right, it's not very difficult to think about it intuitively. You just have to create a table. For example, let's say you have a set S, which is S0, S1, so infinite, another set. So let's just look at S cross T. And you have to write a table out of it and then give an ordering in which you can list the elements of the table. So you have S0, T0. Similarly, you have S1. Now, because S and T are both countable, the number of rows and number of columns in this table are countable. That's where you use that S and T are countable. And you know that every element of S cross T is somewhere in this table. So you can just keep assigning numbers to the elements in this table, and everything will be listed. It might be difficult. But there is one most natural thing that you try to do. If I give you mn, what is the most natural function that you try to do to get this to the set of natural numbers, which could be a bijection? Let's see if someone gets it. You can just use some fundamental theorem.
2 power m into 3 power n.
This one, right? Because every number has a unique prime factorization. This is the most natural thing to do. 2 power m, 3 power n. Then you can try to show, is this a bijection? This is certainly injective, right? For example, if f of m is equal to, let's say, f of m prime, we have 2 to the n, 3 to the n. So this means that m minus n prime is equal to n minus n prime. So m and n prime and n and n prime. So this is an injection, but is this surjective? So that you have to see. Or should you do some massage to make it surjective? Right? So the Cartesian product of countable sets is countable. So that is one observation. ST are both countable sets. So corollary of this would be that n cross n is countable. And this would also mean that Q plus is countable. But actually, one might think, right? It's very easy to show injective functions, usually. It's a bit difficult to show that functions are surjective. So maybe even injectivity, is it sufficient to show that it is countable? It's very natural. Suppose I give you a question and you're not able to show that there exists a bijective function. Not able to show in the sense, you are trying hard for several days, you are not able to construct one. But an injective function may be very easy to construct, just like what he showed. So is it enough to show that the set is countable? Is it enough to show that there exists an injective? This we will see probably after one of the lectures. That it is actually enough. Right? So even this function itself is a proof that n s cross t is countable. You don't even have to show that the function, the map is such. Yeah, that we will see. So yeah, this is one thing. Okay, I have 10 more. So some more examples. So what do you think you would probably want to do next?
Ma'am, this R positive is what? Positive real numbers or positive rational numbers?
There is no R here. Oh, where did I write? Q positive. This one? Oh, this is Q. Okay, sorry. Yeah, positive set of positive rationals. So yeah, some things about infinite sets are a bit counterintuitive. Like for example, if none of you knew anything about Cantor's arguments, then if somebody gave you the set of rationals and asked you whether it is countable, right, without the definition of countable, can you count and tell me the cardinality? You would have said this is a bit difficult, right? And between any two rational numbers there are infinitely many rational numbers. So how do you order them in any particular way? But surprisingly, it is. It's not even surprising. It's a very natural thing to do, like what all of you suggested. So this is probably the first difference between finite and infinite sets. And some examples of countable sets we have seen. So what is the next possible set that you can think of? Somebody said primes, but yeah, in this hierarchy.
Infinite sets that aren't countable.
So this is countable, sorry, I missed. So what can you say about reals? Right? It's the set of real numbers countable. Seems like because rational is also infinite set, we thought between any two rational numbers there are infinitely many rational numbers. But even then we were able to come up with an order. So can you do this for real numbers? So that is one question. But this we will answer in the next lecture. Okay, we can try to keep this. What do you think it should be? It should not be. Okay, so this is something I wanted to say. And set of primes somebody had asked. I'm not sure if we will do the proof in class, but so a subset of a countable set is countable. We can try to do this in class actually. It's not hard, but still, maybe in the next lecture. So a subset of a countable set is countable. So this means that the set of primes is countable. Can someone say what you would? So set of rationals is countable. What would you think about the set of irrationals? So irrationals are reals that are not rationals. This is real science. So these two sets seem to be like different, right? I mean, seem to be the only things that we have not seen so far. The rest of them we have seen, at least in this list. So primes, because we know that subset of countable set is countable. Okay, so now what is the first thing that would occur to you about R minus Q? What is the relationship between R minus Q, R and Q?
Ma'am, if R minus Q is countable, like if we could prove R minus Q is countable, then R is also countable. Like if we just proved that Q is countable, then Q union R minus Q will be countable.
Is equal to R, right? So this we know is countable. So what are you saying? That if R minus Q is countable, then R is countable, is it?
Yes, ma'am.
But we don't know if the union of countable sets is countable, right? Yet. Right? That will require that the union of countable sets is countable. Right? So these three questions we will see in the next lecture. That's what I want to say. The answers to these three questions. But what he said is true. If the union of countable sets is countable and our set of irrationals is countable, then the set of reals is countable. So
Finite union of countable sets are countable, but then
okay. So
countable union isn't.
Yes, yeah. So
it can also prove that irrationals are uncountable because irrational can be considered as the set of all limit points of the rational. So all the set of rational forms an uncountable union of that countable number of sets. So that's uncountable, I think.
Yeah, but these things will assume that you already know how to show one of these are uncountable, right? Like you know that reals is uncountable.
Yes.
Yeah, that's what. That is something we have not told the class. So it's countable union. That's what. So what he's saying is, if there are only like 10 sets, each of which is countable, then it's clear that it is countable. Like you assign numbers in the order. You keep assigning this, and wherever you left, you can assign it. You can just write a table, just like what we did. Set S1, S2, S3, and then you can order the elements like this. But if it is countable union of countable sets, then this is also an infinite series. Then how do you? Okay.
Ma'am?
So,
We could show that R minus Q is not countable.
sorry.
We we could show that R minus Q is not countable by noticing that irrationals have infinite non-recurring decimal expansion. So we could if they were countable, and we could we could sort of take a list of those countably many irrationals, and we could consider a different irrational that differs in with these with at least one of these with every single element at least one place. That would enforce that this irrational is not in our set, and hence irrationals are not counted.
Okay, so are you coming up with this argument in the class? This is the first time you've seen this?
I actually saw like a vague proof somewhat. I've heard the idea.
Yeah, that is So if you haven't seen this for the first time, then it might be very astonishing. If you have already seen some flavor of this, right, which you may have in POC. I'm not sure if you've done the theory of computation course or automata course. Yeah, this you may have seen in the halting problem argument, showing that there are unsolvable problems that exist. That is true. So what he said is exactly what we will do in the next class. It's called Cantor's diagonalization argument. We want to see if all the reals can be counted. We'll see some more advanced theorems of Cantor. So maybe I will stop here, or maybe I will post one more question and stop. So if you look at the set of natural numbers, right, let's just look at them. So you can define for any set A, let's say A, B, you can define the power set of A to be the set of all subsets of A. Right, so this has 4 elements. A, B, A, B. So now the question is, how does the cardinality of power set of A relate to the cardinality of A? If A is a finite set, let's say it has n elements, then this has 2 to the n elements. So for any non-empty finite set, the cardinality of the power set is definitely greater than the cardinality of the set. Now we can define the power set of natural numbers, which is the set of all subsets of n. So this has everything. The empty set of natural numbers itself, all singletons, and so on. Now, what can you say about the cardinality of the power set of natural numbers? Right? So, is this set countable essentially? Can it have so in the finite setting, at least the power set of a set does not have the same cardinality of the set itself. What can you say about infinite sets? So essentially, what is the cardinality?
Is this countable?
Is this countable? Yeah. Want to see your guess?
Yes, I'm actually guessing. But the direction I was thinking of is just concatenate the elements of the subset to get like a actual natural number. So that is.
What about this? What about this? So 1, 2. So you have the set 1, 2. So that will go to the element 1, 2 is what you say.
It will go to 12. Yeah.
Okay. Yeah. So then there might be some problems. For example, that may not be a bijection, right? Is every natural number in there? You have to figure out.
No, but if it's a subset or if it's an infinite subset of the naturals, then it's obviously also countable. Clearly, it is a subset of the naturals. Even though even if we don't get all the naturals, we will get at least an infinite subset of the naturals. And that, like any infinite subset of the naturals, is countable.
No, but like, what would the concatenation of a natural number, I mean, of the set of natural numbers or odd numbers be? All those would be just infinite.
I don't think you can, like, are infinite subsets allowed?
Yeah, I think so.
Oh.
Yeah, when you say power set of natural numbers, right? All infinite. Right. Yeah, so that's what I said, right? So n is sitting inside. What do you mean by is that allowed?
No, okay, then it doesn't. Then it doesn't.
So that's a question. Or is P of n countable? Let me put it that way. So yeah, these are the questions. It is not required that you solve these questions at all. We will solve all the questions. But we want you to think about it and try those exercises. Please don't solve these questions. Then you don't have to attend the next lecture. So we will solve them together. And we'll also see some more advanced topics on these, the cardinalities, estimating the cardinality second sets. Okay? Also, to what you said, what would the empty set then do? Maybe 0, but then. Okay, so maybe I will stop there. But if there are questions, I will just stop there.